Okay. I think it's going.
Yesterday I just tried to match the I just tried to match with Dr. Bradley class because yeah, it doesn't work for me, so I just changed that to my
You changed to be like plus plus on the
yeah, I changed it to plus plus.
For whatever reason,
Like an
trans
integrate.
control circuit just broke. Or it was not finite, and it wasn't that anything was wrong. It was just not
Like a point. It says specific time point. The value is not finite.
Yeah, wait. Did you get the sigmoidal thing to work? Did you get it? You did?
Yeah.
Huh. It's hard to study.
I asked you. You want me to read because I just
What? How many? Like how many were there in the last one? Oh, it ends at 4. Like counting the tasks. Like, there's only one homework problem. That has 4 sections. That's great. Or no. Oh, wait. You just numbered the last thing. Instead of 6. Which doesn't necessarily mean anything.
So you like class?
But definitely.
I'm going to be. Okay, let's get going. So we can do more stuff. Okay, so last time we did this sort of quick prep to talk about nodal analysis, right? And the fun part is now what we're going to be able to do is look at some detailed sort of applications of nodal analysis for medium and larger scale mechanical systems. So it's easy to think about when we're doing onesie, twosie little masses and springs and stuff, and now we'll start doing it with larger problems. So what we're going to do is we're going to learn how to use the MATLAB eigenvector function for solving these problems. We'll obviously, we'll verify that what the math we did on the board the other day was correct. We'll use Simulink now to start making more scalable architectures, basically for thinking about multi-body system dynamics, so that we can, we'll basically start sort of fusing Simulink and cutting and pasting, and whatever else we want to do to be able to get the answers we like, to make large-scale models. And then let's talk about doing this for larger mechanical systems, and the homework will be sort of take this to the next level by thinking about random variations and its effect on system vibrations. So, the idea here is then like this is analogous, of course, to the problem that we did on the board the other day. Where we can say for a multi-degree of freedom system, which basically means we sort of have two second-order systems there. There's 2 ways that they can sort of vibrate. We can do our analysis with our eigenvector problem, eigenvalue problem, and we're able to derive through these mode ratios and natural frequencies these preferred free vibration patterns. So if we talk about, obviously, like this 2 degree of freedom system, it's got 2 masses and springs in between each mass and the wall on this side. And we want to apply some force input to mass 1. Then we end up with the equation of motion look like this, right? So the mass that is on x, mass 1, x double dot 1, is acted on by 3 sets of forces. 1 is due to its own motion, so if everything else is still, it has sort of 2 springs that act on it, the one in front and the one in back. But also, if this is pulling, then mass 2 is moving, then it has a spring that pulls it as well. And it also has an F1. The same sort of thing was happening for the second degree of freedom, for the second mass there. So last time we obviously we calculated the natural frequencies and did all this kind of stuff by solving the classical eigenvalue problem, where we have the spring, the stiffness matrix, the mass matrix, the amplitudes. In this case, a free. We're gonna this the eigenvalue problem is it has no forcing, so it's a free response. And what we found last time was that the natural frequency of the system, omega n squared, were equal to the eigenvalues, which have value of k over m and 2k over m. And mode ratios were this phi, which is a vector of mode ratios. Amplitude 1 over amplitude 2, we had 2 possible conditions. One was a 1-1, in which case they were both vibrating in the same direction, and a negative 1, positive 1, in which case they were vibrating in opposite directions, right? The nice thing is now we can basically use MATLAB to help us perform these calculations for any set that we might like to. Let's start by changing this number of masses here to just make it 2 to start out with, so we can make this easily visualized. But you should be able to copy and paste this whole code into your MATLAB script, and I'll take you through it and show you what it does. First thing it does is, closes the window, sets whatever the values of k and m that you would like to have happen here, number of masses, and then I say basically it composes the mass matrix and the stiffness matrix. It says for I equals 1 to the number of masses, basically just set the diagonal of the mass matrix equal to whatever that mass is. So you'll remember that our pattern from when we did this in class was that if we had a mass matrix that was a 2 by 2 mass matrix, it had a diagonal that was equal to m and all the other things are 0. So purely diagonal matrix, right? The K matrix, the stiffness matrix, what had values that was along its diagonal, it had, I don't know, it was minus or positive K. Right, but it's, yeah, so K sub I is positive 2K, minus K, minus K. Right, so that's all this does, is it composes it's a 3 wide diagonal matrix that has all of, that has these characteristics. So the diagonal is always 2K, and then up 1 and down 1 from each of those is minus K. Right, and that's directly comes from our equations of motion here. So now I'm using the MATLAB EIG function. It acts on K, you just have to give it K and M, and it outputs phi and lambda. Phi is the vector of the mode ratios, and lambda is the natural frequency squared, or the eigenvalues. In this case, I plot them and label them and all this kind of stuff. And you should end up with a plot that looks like this. So I have 2 mode shapes because I have 2 sort of lines here, and maybe it would be good if I'll put little markers on this just to make it so that we can have something to look at. So here, basically what we end up with is this is the net for each one of our masses. We have an associated mode ratio, and the first one is above the blue line basically, and you can see that it has a value of minus, it turns out it's 0.707 and minus 0.707. This is exactly equivalent to, I said that of course the mode ratios for A1, A2 for our problem, we're going to be, the first one is going to be plus 1, plus 1. This is equivalent to whatever to 0.7, 0.7, even if they have negative signs. It's the ratios are what counts, obviously, right? The value depends on the initial condition. If you displace them at 1 meter, then they will, and they're undamped, then of course they'll return to 1 meter every time. If you displace them a centimeter, they'll return to a centimeter every time. Right? So in this case, MATLAB actually just it normalizes it so that the norm of this matrix of this vector is always equal to 1, right? So that's it. So 0.7 squared plus 0.7 squared plus 0.7 squared square root should equal 1. The second one, the second mode ratio is plotted as this -1, +1. So in this, or negative 0.7, positive 0.7. So in that case, again, the idea is that we have another phi here that is associated with the second, or in our case we call it B or something like that. Doesn't matter. It's just still the ratio of amplitudes, and this is -1 plus 1. It's again, the only thing that matters is that the mode ratios are always presented as ratios because it just depends on whatever the initial conditions are. Okay, so what we got to think about here is we have two different modes of vibration. The first mode of vibration, of course, happens at, this one is associated with omega 1, which is equal to the square root of k over m, is our natural frequency. The second one is associated with the natural frequency in the second, which is square root of 3k over m. But the idea is that we have two natural modes of free vibration for this system. If we just give it some initial conditions, it will vibrate in these two modes. It will have either one way that it goes back and forth, together and coordinated in the same amplitude, and that happens at a natural frequency of square root of k over m. Like this. If they do this, it happens faster, and it happens in opposite directions, and it happens at the square root of 3k over m. In our problem, because I gave MATLAB k and m both equal to 1, I end up with these lambdas that are 1 and 3, so that the natural frequency is going to be added to the square root of 1 k over m, square root of 3 k over m. Okay? So now let's try, for example, do the exact same piece of code, but let's make 10 masses just to make it interesting. I'm going to copy and paste in there, and I got a whole new figure. Oh, this is really new. It's easier to read. So now, let me draw the idea here. Let me draw what we're talking about. I just changed the number underscore masses equals 10. So now I have this crazy problem that looks like this, right? I mean, spring, 10 of these guys, right? And on the other side here, it's sprung to the wall. And on the other side of this guy, it's sprung to the wall. Does everybody see how that goes? 10 of them. Okay. So now, how would this thing vibrate? Like, its lowest mode of vibration is what it calls the lowest natural frequency is what we find in here, and has a value of 0.0810. I'm going to erase this stuff here. So our first natural frequency, I'll call it omega n1, is equal to 0.0810. That's the number I just put up there. Square root of that, k over m. And in my case, k and m are both equal to 1, so it sort of just works its way out there. Now, in this case, I have, of course, associated with this some phi 1, that is the mode ratios A1, A2, A3, A4, to A10. is a vector of all of those mode ratios. And I want to plot them for each of our, those are the amplitudes of vibration of all of the masses. So let me go here and I can tell which one it is. This one is the, I'll make it wide or something like that so y'all can see it. But this is the first plot. In that way, I always plot the first one blue, right? So I can tell. And what's happening here is that the middle masses, of course, have high amplitude movements. The masses that are at the end have lower amplitude movements, but they still have some amplitude movements, of course, right? Because they're also sprung to the wall. And so what's happening is I'm ending up with this funny thing where, you know, if I plot this, they're kind of going whoa, 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 you know, together as a big, slow-moving, stringy, springy thing. Okay, can you visualize that? You know what I'm saying? Kind of. Think about it like our vibrating string, right? It's this exact same analogy with vibrating string. That the string in the middle is moving lots because it's the sum of all the displacements of all the other little springinesses, right? The ones at the end are not moving as much because they're only acting under their own compliance to the walls. But okay, right? So everything's kind of like moving as a big like thing. Now let's look at so that's what that mode shape tells us. It tells us the amplitude that is associated with the natural frequency 1, that is associated with mass 1, and mass 2, and mass 3, and mass 4. So I can kind of visualize it through these mode shapes. Here's the second one. Here it is. Okay, what's going on here? It's getting weird. Not really, right? Maybe it's what you would expect. Think about our string problem again, right? This is the natural frequency has something that's associated with 0.3175. So omega n2 is the square root of 0.3175. It has some amplitudes associated with it, a vector of amplitudes. That vector of amplitudes is right here. So now what's happening is I'm ending up with these sort of now, you know, a wave, but it's a wave in opposite directions. So now what's happening is that they're going whoa, 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 right? This is my favorite part of this class. I can see it, and I can see it happening. Wow, like whoa, whoa, right? Okay. So what's happening is the ones in the middle. Number 5 is, in this case, would be number 5.5. The ones in the middle are moving a little bit, just a little bit to the side, and in opposite directions. And the ones in the ends are moving a lot and in opposite directions, right? So it's going like, wow, wow. So, and I can, one can go on and on and on. We go to mode shape 3. What do you expect to see happening in mode 3? It looks like this. All right, now it's got, now I run out of hands, but it gets, the ones on the end are moving out, the ones on the middle are moving together, like, wow, it's crazy, it's crazy. Yeah.
It's like every mode you get like a new peak, so one only had like 1 peak, 3 had like 3 peaks, like keep doing that.
Yes, until you get to 10, and in 10 it has, basically what's happening in, let's do in 10, you end up with every one of them is moving in a different direction. They're all fighting each other. So you can imagine they're moving now really fast. I can tell that because the natural frequency of the 10th one is higher natural frequency, right? Lower period, higher natural frequency. And it's higher by a factor of almost, of 50 or something like that.
Right.
And so now in this one is going in, number 6 is going in the opposite direction of number 5, which is going in the opposite direction of number 4, which is going in the opposite direction of number 3. They're all going like, fighting each other every single second of every single one, right?
So I guess would that be kind of like a higher energy state then? So like when you start putting energy in the system, you start to go to the higher modes?
Not necessarily. It's not energy. It's not higher energy. What it is, it's a higher natural frequency.
Okay.
So if you, like, you know, so the idea is, like, if I hit this with a hammer, and you guys know that if we hit, you know, if we put a step function into this or something like that, or hit it with an impulse, what would happen is we would excite all natural frequencies. It has infinite infinite content in natural frequencies. And so all of these would become excited in a string. If you hit a guitar with a hammer, all of the strings vibrate, right? They all go, right? If you hit it at a particular natural frequency, like you pluck it or something like that, right? Then you excite one of these natural frequencies and you get a note, a tone, right? Like a single note or single tone. The same thing would happen with this, right? If I have a beam that's about 2x4 or something like that, and I hit it with a hammer at the end, it's going to go, you get all these natural frequencies being excited. If I you know, only pluck, or if I only do something where I'm just putting in a single natural frequency, then I will only excite it at that single natural frequency. So that's a characteristic of, it's an important point, it's a characteristic of linear systems, that if you excite it at a single frequency, you will only get out content at that frequency. That's a linear system. There's no other ways to do it. So even if I excite this system at something that is not, you know, if I excite it at something that is not one of the natural frequencies, I will not get back this perfect shape. I will not get back that frequency. Okay, so that's sort of a roadmap there. Now let's talk about what we could do to simulate these small scale systems. And let's do it, the objective now is we'll do it in Simulink, okay? So this is the exact same equations for our problem, or whatever you might like to do. And we have a force, we have some masses, we have springs, etc. So what I want to do is I want to make a, we could obviously do our sort of, you could find a transfer function, doing all this kind of stuff like that. That's great and all, but what we want to do is we want to, in this case, we want to use Simulink to help us to do this. So what I propose is let's make a model here, and I'm going to do it very generic, right? So I want to have some mass, I'm going to call it, whatever. I'm going to, in the first case, we're just going to basically make it so that all the masses are the same. And okay, so I sort of want to, you know, do like the dot dot dots on this side and do the dot dot dots on the other side here too. So we're going to call this one mass of I, this one mass I sub I plus 1, I minus 1. And I'm going to apply a force, F sub I, to this mass, and I want to be able to derive the equation of motion for this system. But my objective is to be able to do it so that I can, write it in Simulink and be able to do some modeling, whatever. Okay, so in this case, I basically end up with an equation of motion that looks like this, right? So here's sum of the forces is equal to m sub I, x sub I double dot. And the sum of the forces on this thing are going to be, of course, F sub I, so it's positive in the, you know, in our sort of like X sub I direction, minus 2k times X sub I. So if this mass displaces a little bit in this direction, then it will have a doubled restoration force, plus if m sub I or x sub I plus 1 goes in that direction, then I have a force that is x sub I plus 1. And I have a k x sub I minus 1. So basically, if I just place this one in the positive x minus I minus 1 direction here, then it pushes this mass in the positive x direction, right? So all I have is, 1, 2, 3, 4 terms that will let me be all the forces on this mass and this x. I don't know. Okay, so now if I solve this for x sub I double dot, I get k, right, plus 2k x y plus k xy plus 1. And then plus f sub I over m, and this whole thing is over m. Okay, so now what I want to do is I want to make a model of this in Simulink. And I'll give you guys the kind of the roadmap for it right here. So let's all pull up Simulink and we'll try to code this problem up in 5 minutes of effort, hopefully, okay? Shouldn't be too big a deal, but let's give it a shot. We're going to make good use of our subsystems, right? And I'll just show you the way I'm going to do it. X double dot sub I. K over M. Right, so what's our strategy here? Same as always, this is a second order system. So I'm going to try to have an input here of x double dot. I have a dot. And over here will be x. And I'm going to call that my actual output here. In this case, I'm going to just make it easy on myself by doing this user-defined function thing that will let me just write a little MATLAB code in there. Fix that. Now, my objective is to write my equations the way I have it on the board, which just takes a little bit of effort. So I'm just going to call k, we already have k and m defined. So looks pretty good to me. Very good. Okay, so now, hopefully, let's just say, I should now basically be able, this is my dynamic subsystem, mass, call it mass 1. And so let's just see what might happen. If I, for example, put in, I'm going to start putting, I'm going to make this so that I'm going to call the displacements of everything else. 0, and basically rely entirely on initial conditions to put any dynamics in there. Let's just make sure that it kind of puts out some second order-ish behavior. So I'll provide an initial condition here of, I don't know, 0.1 meters. A little bit of luck. Response. Does everybody follow what all these things are doing, right? I'm just basically saying, in this case, let's attach this mass to 0. Let's attach, let's glue this one to the ground, and glue this one to the ground, and let this little guy vibrate in between there. That's my subsystem, yeah. Shouldn't matter too much if it's gray or blue.
Did one of your integrators in the initial condition?
I did. I put a 0.1 meter initial condition on the integrator by double clicking in here.
Yeah. And then your first integrator block would be 0.
Yeah, that just means I have 0 initial velocity. You go with that in there. You did when you copied it.